Hi class, good morning. So this is the first topic in Thermodynamics 2. Okay, so this is under the properties of steam. Okay, so by the way, so let us first define some terms in this topic. Okay, so we have here saturation temperature. So saturation temperature, this is the phase change temperature corresponding to the saturation pressure, sometimes called the boiling temperature. Okay, so let us consider an example. So in this definition, so water boils, of course, at 100 degrees Celsius, and of course at a pressure of 101.325 or atmospheric pressure. Okay, so take note that water will not only boils at 100, so it depends upon also to the pressure corresponding to the temperature given. So another example for B, so water boils at 179.91 degrees at a pressure of 1000 kilopascal. Take note class that the water here is a pressurized water. Okay, so take note that water will boils at 179, which is uh, quite far, of course, from 100. Okay, so another steam water condenses at 311.06 degrees Celsius at 10 megapascal. Okay, so meaning the steam will condense, will turn again into water at 311 at a pressure of 10 megapascals. Okay. Or steam condenses at 39 degrees at 0.007 megapascal. So if you take the consider the table, of course, steam table. So table 1. So you will notice that the for a given temperature, there is a corresponding pressure given, which is the saturation. Okay, the saturation pressure or the temperature. Okay, so always class use steam table. Okay, another we have here saturation pressure. So the phase change pressure, or another is the compressed liquid. So liquid whose temperature is lower than the saturation temperature, sometimes called subcold liquid. Okay, so take note class of the term. Okay, compressed liquid. Okay, so later we will consider, of course, the diagram in order for you to locate the term used. Okay, so example, so is liquid water at 110 kilopascal and 100 degrees Celsius a compressed liquid? So that is class the question. Is this given water a compressed liquid? Okay, so use class the steam table. Okay, table 2. Okay, P saturation at 100 degrees Celsius is 101. Okay, so meaning class, the water will boil at 100 degrees Celsius at also 101.325 kilopascal. Okay, so if you look at the saturation temperature at 110 kilopascal, you will notice that the value is greater than 100. Okay, greater than 100 degrees Celsius. Okay, if that is class the case, the water is at a compressed liquid. Okay, state. Okay, the water is compressed, or the liquid is compressed. Okay, so another we have here saturation liquid. Okay, liquid at the saturation temperature corresponding to the saturation pressure. Okay? So, it is a pure liquid. It has no vapor content. Okay? Okay, example class. Liquid water at 100 and 101,325 kilopascal. Okay? So, another is liquid water at 233.9 and 3 megapascal. Okay? So, take note class. You look at table 1 of the steam table. Okay? So, you will see this value there. Okay? So, for letter C, liquid water at 324.75 and 12 megapascal. Okay? So, again, from steam table, okay, so T saturation at 101.325 is 100. T saturation at 3 megapascal is 233.9. And T saturation at 12 megapascal is 24.75. Okay? So, the given class or the example at the upper portion, of course, utilizes the table 1, and this example B utilizes table 2. Okay? So, take note class. Okay? So, take note class, steam table is composed of 4 tables. So, table 1 is a table for saturation temperature. Table 2 is saturation pressure. Table 3 is vapor. And table 4 is for compressed liquid. Okay? So, another class is saturated vapor. So, a term including wet and dry vapor. Dry, saturated vapor. Okay? Vapor which has just completed evaporation. Okay? So, the pressure and temperature of vapor are the saturation values. Okay, example, steam or water vapor at 100 and 101.325. Okay, steam at 212.42 and 2 megapascals. And so on and so forth. Okay, so another is wet vapor. So, the mixture of saturated liquid and dry vapor during the phase change. Okay, I think it is clear. Okay. Another is superheated vapor. So, vapor whose temperature is greater than the saturation temperature corresponding to the pressure of the vapor. Okay, so another example is steam at 200 degrees Celsius and 101.325 kilopascal. Okay, 200 degrees Celsius greater than the saturation temperature at 101.325, which is 100. Okay, as previously shown. Okay, so meaning the sample is superheated. Okay, so another steam at 305 megapascal. So take note, 300 degrees is greater than the T saturation of at 5 megapascal, which is 263.99 only. Okay? Okay, so next, we have here degree superheat. Okay? So, degree superheat is the term used for the numerical amount by which the temperature of superheated vapor exceeds the saturation temperature. Okay? So, take note class, if you are going to calculate the degree superheat, use this formula. So, degree superheat is equals to the actual superheated temperature minus the saturation temperature at existing pressure. Okay, example class. So, determine the degrees of superheated steam at 200 and 101 kilopascal. Okay, take note class, the temperature at 101 is 100. Okay, so therefore, the degree superheat now is 200. Take note, this 200 is the actual temperature of the superheated steam minus the saturation temperature at 101.325, which is now equals to 100 degrees Celsius. So, take note class, that is the degree superheat. Okay? So, another we have here the degree subcold. Okay? So, degree subcold of a subcold liquid is difference between the saturation temperature for a given pressure and actual subcold liquid temperature. Okay, class. So, again, use this formula. For degree subcold, that is equals to T saturation at given pressure minus the actual liquid temperature. Okay? So, example class. So, determine the degree subcold of a liquid water at 90 degrees and 101 kilopascal. So, take note class. The saturation temperature at 101 is 100 degrees Celsius. Even if you look at this at the table 2 of the steam table. So, take note now, the degree subcold is equals to the saturation temperature minus the actual temperature of the subcold liquid. Okay, so therefore, class, the degree subcold now is 10 degrees. Okay. Another is subcold liquid. So, a subcold liquid is one which has a temperature lower than the saturation temperature corresponding to the existing pressure. Okay, example, liquid water at 60. Okay? And 101 is subcold liquid. Okay? Why? From steam table, the saturation temperature at 101 is 100. Since the actual temperature of water is 60, which is less than 100, therefore it is a subcold liquid. Okay? Another class, we have here the quality. Okay? Quality. So, it is class designated as X. So, the quality of wet vapor or wet steam is the percent by weight that is saturated vapor. So, percent moisture is Y. Okay? Designated as Y. So, the percent moisture of wet vapor is the percent by weight that is saturated. Okay? So, take note class that the mass of the saturated vapor plus the mass of the saturated liquid is of course the total mass. Okay? So, mass of the wet vapor. Okay? Okay, so by definition, okay, so determining X now is equals to mass of the quality, of course, equals to the mass over the total. Okay? Mass of the vapor over the total mass. For the moisture, we have here the mass of the liquid divided by the total mass. Of course, we multiply it by the 100%. Okay? So, that is the formula. So, another, we have here the latent heat of vaporization or hidden heat. Okay? So, it is the amount of heat required to convert water at a given temperature and pressure into steam at the same temperature and pressure. So, there is no change class of the temperature, of course, and the pressure. Okay? But, the phase, of course, changes. Okay? Or change. Okay? So, it is expressed by the symbol HFG and its value is available from steam table. Okay, so the value of the latent heat is not constant and varies according to pressure variation. Example, okay. Take note class. So, at 100 degrees Celsius, the enthalpy or the hidden heat is equivalent to 2257. Okay? Or the latent heat of vaporization. At 200, that is 1940.7, and at 300 is 1404.9. So, okay. Another, we have here the sensible heat. So, it is defined as the quantity of heat absorbed by 1 kilogram of water when it is heated from 0 degrees or freezing point to boiling point. So it is also called total heat or enthalpy of water of liquid heat invariably. Okay? So it is reckoned from 0 degrees where sensible heat is taken as 0. If 100 kilogram, 1 gram rather, kilogram rather, of water is heated from 0 to 100, the sensible heat added, it will be, of course, the uh, specific heat multiplied by the temperature change, so which is 418. But if water is at, say, 20, so initially the sensible heat will be 100 minus 20 multiplied by 4.18. So this type of heat is denoted by letter H sub F. Okay? And its value can be directly read from the same tables. Okay? So another, we have the Tripol point. Okay? So it's merely the point of intersection of sublimation and vaporization curves. Okay? So it must be understood that only on PT diagram is the tribal point represented by a point. Okay? So on PV diagram, it is represented by a line. Okay? And at internal energy at volume diagram, it is represented by a triangle. Okay? So the pressure and temperature at which all three phases of the substance coexist may be measured with the apparatus that is used to measure the vapor pressure. Okay? So it is, class, very difficult to just imagine without looking at the diagram. Okay? So another class, we have here the critical point. So we have here the limit of distinction between a liquid and the vapor, or the pressure at critical pressure is the pressure at critical point. Critical temperature is the temperature at critical point. Okay? So another, we have here a term gas. Okay? A vapor whose temperature is greater than the critical temperature. Okay? Okay, class. So we have here the illustration. Okay? So the change of water from a subcold liquid to superheated vapor, class. Okay? So take note that here, at the first illustration, the pressure is 1 atmosphere. Okay? So that is liquid. So the temperature of the liquid is 40. Okay? So if you look at the steam table, the liquid here is at subcold liquid. Okay? So another, we have here at 100 degrees. Okay? So the liquid now expands. Okay? So again, the temperature, the pressure rather, is 1 atmosphere. Okay? So and then we have here vapor. So this is a mixture of vapor and the liquid. So at 1 atmosphere also. So take note that the volume occupied is greater. Okay? And then converting now the liquid here to a complete vapor. Okay? So take note, class, that the volume is greater, okay, as compared to the previous one. Okay? So again, take note that the pressure inside the cylinder is 1 atmosphere also, but the temperature again is at 100. Okay? So for a superheated now, so of course the temperature is greater than 100, so there is a degree superheat. Okay? Of course. So take note that the volume again increase from the original vapor here. Okay? Original volume occupied by the vapor. Okay? So another, so let us now, class, consider this pressure volume diagram. So we have here a line. Okay, so the designated broken line at the right portion, that is saturated vapor. meaning complete or 100% steam. So if it touches the right portion uh, of the line, okay? At the left broken line here, or yes, that is a liquid, okay? So liquid. So at the, of course, the upper portion of this saturation line is the critical point. Okay. So if the steam class is now beyond the broken line at the right portion, it is now a superheated steam class. Okay? Superheated steam. And if the location, of course, uh, of the steam is inside the saturation line or curve, in between the broken line at the right and left. So meaning class, the steam is in a form of a mixture of liquid and a gas. Okay? A mixture. Okay? So take note, class. Okay? So another, we have also here the TS diagram and PV diagram. Okay? So we have here at the left portion, we have here the compressed liquid. We have here again the saturation line. At the upper portion is the critical point. Okay? So take note, class, this is the constant pressure line. So this broken line here. Okay? Constant pressure line. Okay? So at PV diagram, again, the same. You have here the compressed liquid, superheated vapor, critical point, and then the mixture at the inside portion of the diagram. Okay? So another, we have also TS diagram here. So this is somewhat similar class to the previous illustration. So we have here again for compressed liquid, it is at the right or the left portion, of course, of the diagram. So this is the saturation line, class. The saturation line here. Okay. So critical point again at the upper portion. And this line here is the constant pressure line. Okay. Okay. So take note, class, of the subscript used, okay, or symbol. So for F class, that is properties of saturated liquid. G, properties of saturated vapor. Fg is the change of evaporation, meaning mixture, okay. B is the specific volume, S is the specific entropy, U is the specific internal energy. Okay, so for the formula, class, the enthalpy or the specific volume of the gas is equals to the specific volume of liquid plus the specific volume of the mixture. Okay, and so on and so forth. Okay, the same class for enthalpies, for entropies, and internal energies. Okay, so another, we have here, class, the formula. Okay, so and determining the, let's say for example, for the specific volume. Okay, we have here the specific volume is equals to the specific volume of the liquid plus the quality of the steam, quality of steam X, multiplied by the specific volume of the gas minus the specific volume of the liquid. Okay, so that is class. So you can also replace this class if you want to determine the entropy. Just replace this with letter S. Okay, all V will be replaced by S rather. And for the internal energy, you replace also this formula this B by letter U. Okay? And so on and support class. Okay? So, this is very easy. Okay, class, thank you very much. Okay? So, I think if you read or watch this video class, you are ready to answer the question that I am supposed to give you. Thank you very much, class. Okay?